Definition: let Xt be a metric space, then the open subsets of Xt form a topology on X called the topology induced by D or topology generated by D. And we consider a metric space Xd and A be a set in X. Then A is said to be open in the metric space Xt provided if we take any element, any point X from A, there must exist an open ball with the center X contained in A. Then we say that A is open. We take all such open sets from X, then it form a topology on X. Then such a topology is called the topology induced by D or topology generated by D. Modern X definition: a topological space X2 is said to be metrizable if there is a metric D on X such that the topology tau is induced by D. That is, a space X2 is said to be metrizable if that topology is induced by a metric or that tau consisting of all those sets which are open with respect to D. Then we say that the space is a metrizable space. Move on to some examples. Show that tau is equal to set of all u belongs to P of R such that for each x belongs to u there exists delta x such that x minus open interval x minus delta x plus delta x subset of u is metrizable. We already shown that tau is a topology, so we have to prove that it is metrizable. So it's given by, we consider R real line, and for any set u and any point x belongs to u, if there is an open interval x minus delta x and x plus delta x contained in u, then we say that u belongs to tau. We have to prove that such tau is metrizable or it is induced by a suitable metric. So here we consider the metric as usual metric. Take D is equal to usual metric on R, and is given by D of AB is equal to, distance of AB is given by absolute value of B minus A. And let tau 1 be the topology induced by D. We take tau 1 as topology generated by D. But here we have to prove that tau is generated by D. So it's enough to show that tau is equal to tau 1. Both topologies are equal. Then we will get tau is generated by D. So to prove tau is equal to tau 1, we will prove tau subset of tau 1 and tau 1 subset of tau. So first we prove that tau is subset of tau 1. So we prove this case first. For this we take a set, we take an open set u belongs to tau and an element x belongs to u. Since u belongs to tau, u satisfies the condition for tau. That is, if you take any element x from u, there exists a delta x greater than 0 such that x minus delta x plus delta x is a subset of u. So we get there exists delta x greater than 0 such that open interval x minus delta x plus delta x is subset of u. Now we can write this open interval as open ball with the center x and radius delta x. It's a subset of u. Let's check what is open ball with the center x and radius delta x. This consists of all those elements y belongs to R such that distance of x and y is less than delta x. This is the definition for open ball or open sphere. This will be equal to set of all y belongs to R such that here D is given by absolute value of B minus A. So here absolute value of y minus x is less than delta x, or this can be written as set of all y belongs to R such that minus delta x less than y minus x less than delta x. So this will be equal to set of all y belongs to R such that x minus delta x less than y less than x plus delta x. So this open ball consisting of all those y values in between x minus delta x and x plus delta x. So this will be equal to open interval x minus delta x and x plus delta x. So this open interval can be rewritten as BD x delta x. So we'll get it is a subset of U. That is, we get if we take any element from U, there is an open ball with the center x and radius delta x contained in U. That means U is open in XD. U is open with respect to the metric, and we know that tau1 is the topology induced by D. That means tau1 consisting of all those sets which are open with respect to metric. Here U is open with respect to the metric D, so we will get U belongs to tau1. Thus we can say that tau subset of tau1. Equation number 1. So move on to its converse part. For that we take an element set U belongs to tau1 and an element x belongs to U. Since tau1 is the topology generated by D, we can say that U belongs to tau1 implies U is open with respect to D, open in XD. Now since x belongs to U and U is open in XD, we can say that there exists an epsilon greater than 0 such that BD x epsilon is a subset of U. So this is the definition for open set in metric space. So U is open in XD means for any point x in U there is an open ball with the center x contained in U. This is nothing but open interval x minus delta x and x minus epsilon and x plus epsilon subset of U. This is already shown that. So choose delta x equal to epsilon. So we will get x minus delta x, open interval x minus delta x plus delta x is a subset of U. This is the condition for tau. So we'll get U satisfies the condition for tau. Therefore we'll get U belongs to tau. Thus we can say that tau1 is a subset of tau. Equation number 2. From 1 and 2 we can say that tau1 is equal to tau. Since tau1 is metrizable or tau1 is induced by D, we can say that tau is also induced by D, that is tau is metrizable. X tau is metrizable space. Move on to another example. Show that tau is equal to set of all U belongs to P of R2. Consider the plane R2 such that for each AB belongs to U, there exists delta such that set of all xy belongs to R2 such that x minus a whole square plus y minus b whole square less than delta square is a subset of U is metrizable. So tau consisting of those sets U such that if we take any point AB from U, there must exist an open circle with the center AB contained in U, then we can say that U belongs to tau. We have to prove that tau is metrizable. So as usual we consider a metric. Here also we consider the usual metric on R2. Usual metric on R2. Usual metric on R2 is given by D of AB is equal to square root of x2 minus x1 whole square plus y2 minus y1 whole square, where A is equal to ordered pair x1 y1 and B is equal to ordered pair x2 y2. So for any 2 point A and B, the usual metric is given by the shortest distance formula, square root of x2 minus x1 whole square plus y2 minus y1 whole square. And here also we consider tau1 as the topology generated by D. Topology induced by D or generated by D. So we have to prove that tau is generated by D, so it's enough to prove that tau is equal to tau1. So as usual we will show that tau subset of tau1 and tau1 subset of tau. So first we prove that tau subset of tau1. For that we take an open set, let U belongs to tau and X belongs to U. An open set and a point Since U belongs to tau, U satisfies the condition for tau. That implies set of all ordered pair xy belongs to R2 such that, x means ordered pair AB, element is of the form ordered pair. Set of all xy belongs to R2 such that x minus a whole square plus y minus b whole square less than delta square is a subset of U. This is the condition for tau, and we can rewrite this as BD open ball with the center AB and radius delta subset of U. Let's see what is open ball with the center AB and radius delta. This is nothing but collection of all ordered pair xy belongs to R2 such that distance of AB and xy is less than delta. This is nothing but collection of all those ordered pair xy such that distance is given by, metric is given by square root of x minus a whole square plus y minus b whole square less than delta, which is equal to set of all ordered pair xy such that taking square we will get x minus a whole square plus y minus b whole square less than delta square. So instead of this set we can write it as open ball with the center AB and the radius delta subset of U. That is, we take any point AB from U, there is an open ball with the center AB and the radius delta contained in U. That means U is open in XD. U is open in R2D. We consider X as R2D. That implies U is open with respect to the metric, and tau1 is a topology induced by D. That is, tau1 consists of all those sets which are open with respect to D. Here we will get U is open with respect to D. Therefore, we will get U belongs to tau1. Therefore, we can say that tau is a subset of tau1. Equation number 1. So, we have to prove the converse part. That is to prove tau1 subset of tau. Here also we take an open set, let U belongs to tau1 and a point AB belongs to U. Now U belongs to tau1 and tau1 is the topology induced by D, means U is open in XD. Tau1 consisting of all those sets which is open in XD. So U is open in XD. Now AB belongs to U means there exists epsilon greater than 0 such that BD with the center AB and the radius epsilon is a subset of U. And as usual, this is nothing but set of all ordered pair xy such that x minus a whole square plus y minus b whole square less than epsilon square is a subset of U. Here also choose delta is equal to epsilon, then we will get set of all x minus y whole square plus y minus b whole square less than delta square is a subset of U. That is, U satisfies the condition for tau. Hence we will get U belongs to tau. Thus tau1 is a subset of tau. Equation number 2. From 1 and 2 we will get tau1 equal to tau2. Next question, show that there are topological spaces that are not metrizable. For that we consider a space with two members A and B, and consider tau as trivial topology, that is empty set consisting of empty set and whole set, that is trivial topology, and let D be any metric on X and tau1 be the topology induced by D. So we have to prove that here tau is not metrizable. Since tau1 is topology induced by D, we have to prove that tau not equal to tau1. For that, given that X consisting of 2 points A and B, therefore distance of A and B must greater than 0, must be positive. That is, if we consider a topological space X tau, and given that A and B are two different points, then their distance must be positive. We take distance from A to B is R. Let D of AB is equal to R. Now we consider open ball with the center A and radius R. Then this open ball, by definition, this open ball consisting of all those points X in X such that distance of A and X is strictly less than R. That means that open ball consisting of all those points such that distance of A and X is strictly less than R. Here B must be the boundary point, and this open ball does not consisting the boundary points because the distance of A and B is strictly equal to R. Here we consider the points with the distance strictly less than R. So this open ball consisting of only one point, that is set A. So we'll get the open ball with the center A and the radius R is nothing but singleton set A. Therefore we can write BD open ball with the center A and the radius R is subset of itself. Every set is a subset of itself, so we'll get BDAR subset of A. That means singleton set A is open in XD. And tau 1 is a topology induced by D. That implies singleton set A belongs to tau 1. In the same way, we can say that singleton set B is also belongs to tau 1. But here we consider tau as the trivial topology, consisting of only two members, empty set and whole set. But tau 1, the topology induced by D, consisting of more than two members, that is singleton set A and singleton set B, empty set and whole set. Therefore we can say that tau is not equal to tau 1. Therefore we can say that tau is not metrizable from tau is not metrizable, or tau is not generated by a metric. Hence we can say that it is not metrizable. There are topological spaces that are not metrizable. Move on to next definition. If tau 1 and tau 2 are topologies on a set X and tau 1 subset of tau 2, for example, let X equal to set A and B, then we can define four topologies. Tau 1 is the trivial topology, empty set and whole set. Tau 2, empty set, singleton set A and whole set. Tau 3 is nothing but empty set, whole set and singleton set B. And finally tau 4, consisting of empty set, whole set, singleton set A and singleton set B. So let tau 1 and tau 2, let we take tau 2 and tau 4. Tau 2 and tau 4 are two topologies on the same set X, and we have tau 2 is a subset of tau 4. Then we say that tau 4 is said to be stronger than tau 2 or larger than tau 2 or finer than tau 2. In the same case we say that tau 2 first set is smaller than tau 4 or weaker than tau 4 or coarser than tau 4. This is the definition. Comparison to, we compare two topologies. If tau 1 is a subset of tau 2, then tau 2 is said to be stronger or larger or finer than tau 1. In the same way, we say that tau 1 is smaller or weaker or coarser than tau 2. So move on to one problem. Let XD be a metric space and tau be the topology induced by D. Tau is obtained by a suitable metric and tau 1 be the finite complement topology. There is tau 1 consisting of all those u belongs to power set of X such that either u equal to phi, u is an empty set, or X minus u is finite. This is tau 1, finite complement topology, and tau is the topology induced by D. So we have to prove that tau is finer than tau 1. That is, tau 1 is a subset of tau. We have to prove this. For that we will take an element, take a set from tau 1 and an element. Let u belongs to tau 1. Let u belongs to tau 1. Then there arises two cases. Case 1 is, first case is u may be empty. U is empty and we know that empty set is open in XD. Therefore we can clearly say that phi belongs to tau. That implies u belongs to tau, in that case we can say that tau 1 is a subset of tau. So move on to the second case. Second case is U is non-empty. U not equal to phi means x minus U is finite. By the definition of cofinite topology, we take U from tau 1. U from tau 1 means U is not equal to phi, that means x minus U is finite. And we know that x minus U is finite means x minus U is closed in XD. Closed in XD. If a set is closed, then its complement must be open in metric space. That is x minus U is open in XD. X minus U is nothing but a U. That is U is open in XD. U is open in XD. That means U is open in XD and tau is the topology induced by D. That means U belongs to tau. In second case also, we will get tau 1 is a subset of tau. Thus, cofinite topology is weaker than tau, or smaller than tau, or cursor than tau. Or we can say that tau is finer than, or larger than, or stronger than tau 1. Then move on to first theorem. Let tau be a topology on X and lambda be a finite set. Then if U alpha belongs to lambda, then intersection alpha belongs to lambda, U alpha belongs to tau. That is, we have to prove that finite intersection of elements of tau is again in tau. For that we use induction, and we define a set S as set of all n belongs to n such that intersection of any n elements of tau is in tau. That is, if U1 and U2 belongs to tau and U1 intersection U2 is belongs to tau, then we can say that 2 belongs to S. In that way we define S. So we use induction on n. So let U1 belongs to tau. U1 belongs to tau means intersection U1 is nothing but U1, that is belongs to tau. That means 1 belongs to S by the definition of the set S. And again let U1 and U2 belongs to tau. And by the definition of topology, second condition for topology, we will get U1 intersection U2 belongs to tau. That is, intersection I equal to 1 to 2, Ui belongs to tau. Then by the definition of S, we will get 2 belongs to S. That is, here we will get 1 belongs to S and 2 belongs to S. Therefore, result is hold for 1 and 2. Result holds for 1 and 2. So we use induction on n. So we assume result holds for n. That is 1, 2, etc. n belongs to S. This means intersection I equal to 1 to n Ui belongs to tau. Now we consider result for n plus 1. Consider the integer n plus 1. Let integral I equal to 1 to n plus 1. Intersection I equal to 1 to n plus 1. Ui is equal to, we can rewrite as intersection I equal to 1 to n Ui intersection un plus 1. And since 2 belongs to S, we can say that right hand side is belongs to tau. That implies left hand side is also belongs to tau. That means intersection I equal to 1 to n plus 1 Ui also belongs to tau. So we will get n plus 1 belongs to S. So by induction hypothesis, the result is true for n plus 1 also. Therefore, we can say that the result holds for all n greater than or equal to 1. Hence, the proof.